Hello everyone, my name is Gautam Dodi and today I'll be presenting on the topic Scalable Big Data Storage Systems. This topic is very important in big data because it helps us understand how really that large amount of data are stored and managed efficiently. Let's begin. Introduction: Big Data and Scalability. First, let's understand what big data means. Big data refers to extremely large sets of data that are complex and keep growing rapidly. It comes from different sources like social media, sensors, and business transactions. Scalability in storage means the ability to increase storage capacity performance easily as more data drives. In simple words, a scalable system can grow bigger without slowing down or crashing. This is very important because modern applications like social media platforms and Internet of Things device produce massive amount of data every second, and we need storage systems that keep up with this growth. Need for scalable storage. Why the challenge? Why traditional storage fails? Traditional databases and storage systems were not built for such huge volumes of data. They face problems like limited capacity, slow processing speeds, and can fail when data traffic is very high. Scalable storage systems solves these problems by dividing and storing data across many servers or storage nodes. This helps data to be saved, processed, and accessed fast even when the amount of data grow continuously. Scalable storage also ensures no single point of failure, so data is safer and more reliable. Key features. Let's look at some important features of scalable storage systems. First is horizontal scaling, which means adding more machines or servers instead of upgrading one big server. This is usually more cost effective and flexible. Next is data replications, where multiple copies of the data are stored in which different places to avoid loss if a machine fails. Scalability systems also offer fault tolerance, allowing the system to continue working if some nodes stop. Elasticity. Elasticity is a feature where the systems can automatically increase or decrease sources based on current data demands. Architecture overview: how it works. The architecture of scalable storage system usually involves a distributed file systems. Here large files are split into smaller parts called blocks. These blocks are stored on different machines or nodes. A central system called the metadata manager keeps track of where each block is stored and manage how data is copied for safety. This distributed approach makes storage faster, fault tolerant, and easy to manage. Popular scalable storage technologies. Some popular scalable storage technologies include HDFS, the Hadoop distributed file system, which is open source and commonly used in big data analytics. Amazon S3, a cloud service that offers unlimited pay as you go storage that's very flexible and scalable. Google Cloud Storage, where which provides fast, reliable cloud storage integrated with Google's other services. NoSQL databases like Apache, Cassandra, and MongoDB, which handle large amount of data with flexible formats and easy horizontal scaling. All these tools can manage petabytes or even exabytes of data by spreading it over many servers. The CAP theorem, understanding trade-offs. In distributed storage, the CAP theorem is an important concept. It explains that a system can guarantee only two of these three: consistency, availability, and partition tolerance. Consistency means all users see the same data at the same time. Availability means the system is always ready to answer requests. Partition tolerance means the system works even if some connection between servers break. Different systems choose this trade-off differently. For example, HDFS focuses on consistency while Cassandra prefers availability. Understanding this helps choose the right system for our needs. Performance and cost considerations. Scalable storage improves performance by spreading the workload across multiple servers, reducing delays and preventing overload. However, using more servers also raises costs, so organizations have to carefully balance between performance needs and budget limits. Techniques like caching, tiered storage for frequently accessed data, and cloud-based pay-per-use models help optimize performance and cost. Real-world applications or use cases. Many big companies rely on scalable storage system daily. For example, Netflix and YouTube manage huge volumes of video data streamed to millions of users worldwide. Banks and financial institutions process billions of transactions every day and with scalable systems ensuring speed and security. Healthcare organizations store massive patient data securely while needing quick access for analytics and research. IoT platforms collect real-time data from billions of sensors requiring fast, scalable storage to support predictive maintenance and monitoring. Future directions and conclusions. Looking ahead, scalable storage systems will become even smarter and faster with innovations like edge computing integration. Edge computing, which processes data close to where it's generated to reduce delay. AI-driven management. AI-driven management tools that automatically optimize data placement and system performance by machine learning techniques. Serverless architectures. Abstraction layer like infrastructure complexity enabling developers to focus on applications while system auto scale transparently. Server architecture that let developers focus on applications. To sum up, scalable big data storage systems are essential to efficiently manage the fast growing data of today and tomorrow, enabling business to stay competitive and innovative. Key takeaways. Scalable big data storage systems are foundational to modern computing through distributed architecture, integrations, and fault tolerance. They enable organizations to harness massive datasets cost effectively while maintaining reliability, transforming raw data into competitive advantage. Conclusion. The foundation of modern data infrastructure. Essential, like, essential for the data economy. In the contemporary data-driven landscape, scalable big data storage systems are not merely advantageous but imperative. They facilitate the efficient ingestion, processing, and analysis of ever-growing volumes of diverse data, empowering real-time insights and strategic decisions making. Architecture cornerstones. The resilience and performance of these systems are underpinned by core architectural principles: distributed storage for parallel processing, intelligent application for data durability and availability, and robust fault tolerance mechanism to ensure continuity operations despite component failures. Catalyst for innovation. These robust storage solutions empower organizations across industries to derive unprecedented value for their data assets. They enable breakthroughs in AI, ML, scientific research, and personalized services. Evolving frontiers. The trajectory of big data storage continues towards even greater efficiency, automation, and integration. Future advancement will likely focus on intelligent tiering, advanced data governance, and seamless interoperability with emerging technologies. Reference. Below is a list of key resources that I used for making this presentation on scalable big data storage systems, like some key papers on distributed systems and the CAP theorem, and the documentation for major technologies like the Apache Hadoop, Apache Cassandra, and MongoDB. Here are the links given of that references, and some textbooks that I followed on online, like these three textbooks that I followed, and some industry reports on big data trends scalability. Thank you for listening. This concludes my presentation.